Okay, this is going to be a long lesson, so I would say go ahead and make yourself comfortable, get a snack, get a glass of wine, whatever you need to get you through this, because it is going to be a while. So for chapter 10, we're going to be talking about the sampling distribution of the difference between two sample means for the independent sample. Independent sample just means that it's not going to have any effect from one population to the next. So that's kind of the high point right here. So the sample selected from one of the populations has no effect or bearing on the sample selected from the other population. Same thing with the independent simple random sample. So each possible pair of samples, one from the population and one from the other, is equal likely to be the pair of samples selected. Again, I'm not going to be quizzing you on the terminology, but it's just something that you should know whenever we're talking about. We want to make sure that it's an independent simple random sample. So now what I want you to do is take a look at our two samples. We have a population of men and we have a population of women. I want you to partner up 2 men and 3 women. So for example, you might pair up Tom and Dick with Danny, Nancy, and Barbara. So that would be one sample. But what I'd want you to do first, before you actually do everything all at once, I want you to just make your pair for men. So list out all the different pairs for men. And then once you have that listed, I want you to write down the different for the 3 women. So you have Cindy, Barbara, and Danny. Then you might have Cindy, Barbara, and Nancy, Cindy, Danny, and Nancy, Cindy, Danny, and Barbara, so on and so forth. So go ahead and create your list for your men and then also for your women. So when you create your sample for your men, you have the sample size of 2 over here. And then for the women, you have your sample size of 3. What I want to show you though is when we're actually putting our independent samples together, we are actually going to be putting them to where it's the selection of 2 men to the selection of 3 women. And we do that each time. So here again, you have Tom and Harry. And you can see we're going to end up getting 12 different possible combinations. And those 12 different combinations are listed in this table over here. So that way it's a little bit easier to follow along instead of just random lines of color. So here we have a total of 12 different samples. And if I wanted to know what is the probability of selecting Tom and Nancy, I'm going to look where we have Tom all right here. We have Nancy, sorry you guys, and Nancy. So what we're actually going to be looking for is where the 2 overlap. So we have Tom and Nancy, 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 Tom and Nancy. So out of our 12 possible samples, we have 6 that contain both Tom and Nancy out of 12. So the probability of selecting Tom and Nancy is going to be 1/2. The purpose behind that was just to kind of get you thinking about two different populations. So here we're going to do the faculty salaries, and it's going to be the faculty salary from a private institution and from a public institution. So first we want to talk about what is the hypothesis test that we might be posing. So we're checking to see, are the mean salaries of the private institutions and the public institutions same or different? So for the hypothesis test, our null is that our average for our first population, our sample population of 1, is equal to the mean salary of the public institutions. So here we're going to have, this is going to be sample 1 we have here, and sample 2 we have here. So our hypothesis is that the two actual salaries on average for the population are the same. Our alternative is going to be that they are not equal. So it's not that one is greater than the other, it's just saying that they're not equal. It also says, suppose that 35 faculty members from a private institution and 30 faculty members from a public institution are randomly and independently selected, and that the salaries are shown below. So there's another thing that I'm looking at. I'm seeing that here we have 35 samples. So here n is going to be 35. And here, n is going to be 30. We know it's a two-tailed test. Both of them are large samples, so we do not need to do the normal probability plot, because remember that magic number for a large sample is 30. So this is just the detailed textbook of the answers we were just talking about from the previous questions. So again, it's talking about how population 1 is going to be the faculty of all private institutions. And then for population 2, it's all faculty of public institutions. Because of the fact that population 1 is the private institution, our mu1 is the mean salary of all the faculty in private institutions. That's why our null hypothesis is that the mean salaries are the same. For population 2, the mean salary of all faculty in public institutions. And our alternative hypothesis is that they're going to actually be different. So we're looking at the two-tailed test. So here it even says, recall this is going to be two-tailed because it's not equal to. And we need to compute the mean salary of our first sample and the mean salary of our second sample. So I am going to go back for just a moment. If you want to pause, and you can go ahead and find your sample means for each of our samples, you may do so. Otherwise, I'm going to go ahead and let you know what those are. So go ahead and pause if you want to calculate it on your own. Our mean for the first sample is going to be 98.19. And keep in mind, this is in thousands. And our means for the sample number 2 is going to equal 83.18. So we can see that there's a difference of 15.01, or just over $15,000, but we're going to check to see with our sample size that we have, so one is a sample of 35, one is a sample of 30, is it actually statistically significant that there's a difference between the two means for those populations? So here's kind of a flowchart of how you're supposed to be doing this. So our whole thing that we just did, we have our first sample, that was the private college. We have our public. We have our means. So again, our first sample mean is 98.19. Our second mean is 83.18. And when it says compare, we can actually say that the difference is 15.01. We're going to need that number for later on in our calculations. So this just goes into how they calculated the mean for the first sample and for the second sample. So again, we have our first sample right here and the second sample mean right there. It's highlighting the difference being just over 15,000, and we're checking to see, is that statistically significant? We'll be talking about whether that is or isn't later on in class. There are a few things that we need to cover first though. So first we have to come up with our different alternative hypotheses. So when it says that the two populations are different, that is just going to say that they're not equal to each other, and we need to recall that this is going to be a two-tailed test. That's going to be very important when you're talking about what your z-values are going to be for the critical value. It's also going to determine which column you're using for your t-value. So if population 1 is less than the mean of population 2, we write it like that for our alternative, and you're going to see it as a left-tailed test. If the population is greater than the second population of the average, we write it where mu1 is bigger than mu2, and it is a right-tailed test. So sometimes we might be creating a confidence interval between the two means. And so one of the things that we're going to talk about is we have 95% confidence interval for the difference between our population means. We'll just say it's between 3 and 5. Okay, so what that means is that we can be 95% confident that the difference lies somewhere between 3 and 5. Okay, so that means that the first average is between 3 and 5 greater than the second average. If we want to be 95% confidence where that difference is between -5 and -3, we say that we can be 95% confident that that difference lies somewhere between 5 and 3 less than your population mean for the second population. We also have what happens when one is negative and one is positive. So if we come up with, we can be 95% confident that it is between less than 3 to greater than 5. Okay, so here again, 95% confident that our difference lies somewhere between -3 and -3 and +5. We would be 95% confident that population 1 is somewhere between 3 less and 5 more than population 2. When you actually get to something like this last one, this means that there may not be a difference. there may be no effect. So at this point in time, if we have one where it's 3 less or 5 greater, then since 0 is an option within there, we could potentially say that it has absolutely no effect at all. So we can't reject our null hypothesis at that point. So case 3, this is where we cannot reject. We may be able to do something like say, well, we may be accepting our null hypothesis because there's not enough evidence to reject it, but we still want to see where those differences could lie. And this could be one of those where, we're talking about quality. So say, actually, perfect example, I opened up a water bottle yesterday, and when I opened up my water bottle, it was literally filled to the top of the container. And had I moved in any direction at all, it would have overflowed and it would have spilt out. So we may be looking at, are we between 3 millimeters less volume than what we need, or are we between 5 millimeters above for our volume? So that might be, when we're talking about how we would make a container for the water, what would we want to go ahead and try to take into consideration where there might be some variation? So how do we notate for 2 different populations? Basically, the notation is still the same as what we've always seen, but for populations, when we have 2 different ones, we have population 1 average, population 2 average. We have the population standard deviation for population 1 and the population standard deviation for population 2. We have the sample mean. So sample mean of population 1, sample mean of population 2. This is the sample standard deviation of population 1 or population 2. And then we have our sample size for population 1 and our sample size for population 2. I'm going to go ahead and quickly write down, don't forget that for these, we're using our z-score. And for the S, we're using our t-score. Because from chapter 8 and chapter 9, some of us are still having some problems identifying which one we're using. So again, if it's that population standard deviation, you'll be using your z-table in the back of the book. If you have the sample standard deviation, or S, that is going to be the t-chart in the back of the book. You do have a question on your assessment for chapters 10 and 11, or I'm sorry, is it chapters 10 and 11 or 9 and 10? 9 and 10. Right here, you're going to actually find the difference between the 2 means. So if you go back to the population of the 2 salaries, we're going to be talking about there's 98.19 for our first population, and then 83.18 for our second population. So you get a difference of 15.01. This is actually the very first question that's on your test when you're testing. So it must be chapters 10 and 11 that we're testing on next. You also will have a problem like this as well, where you're talking about the population differences. With the case of the 2 salaries, we're actually going to be computing off of a sample standard deviation. But just know that this is the equation that you're going to be using when you're trying to find our population standard deviation of our 2 samples. We also have to make sure that both population 1 and population 2 are normally distributed, or the two samples that we collect for our different populations. This right here is going to be very important when you're actually talking about the calculations, but I'm going to let you know right now, you don't have to include this part right here, because our hypothesis test is that the two populations actually have an equal average. So if we're assuming that they have an equal average, that there's no difference, then whatever the mu of population 1 is and the mu of population 2, they're identical. And if you subtract two identical numbers, you get 0. So that's why you don't even have to include that second part of the equation in your numerator. So now we're moving on to the inference of two population means using independent samples, standard deviation, and we're assuming that that's going to be equal. We don't really talk about variance, so you don't really have to memorize or know anything about the equation there. So pretty much what we're looking at though is the pooled sample standard deviation. So anytime you see the pooled sample, you are going to go with your t-chart. That goes with the pooled sample. Okay, and you have a very large equation to find your pooled sample. This is going to be very important when we're calculating the values of our data as to whether we are going to accept or reject our null hypothesis. Because what we're doing is we're taking whatever we get as our sample where it's pooled, we're actually using that in our sample equation. Remember, we're not using mu1 minus mu2 because we're assuming that is going to be 0. So if you do make one error with the pooled sample, it's going to give you another error for the test statistic. I do take that into consideration when grading your assessments as well. So there's the equation again. Remember, we are not going to be finding the difference between our actual population means because we're assuming that's 0. The one that I want to highlight here, though, it says that it has a DF of N1 plus N2 minus 2. So if you recall, if we were only testing one sample, then it would be the sample size minus 1. Because we're testing two samples, we have to add those two sample sizes together, and now we're subtracting by 2. So this is going to be the procedure when we're talking about a hypothesis test with two population means, and that we do not know the sample standard deviation. So we don't know the population standard deviation, or they're roughly equal, I should say. So it's a simple random sample. They are independent samples. So that is that one does not affect the outcome of the other. It is a normal population or a large sample. Don't forget that a large sample, again, that right there, has to be at least 30. Okay, otherwise, if it's less than 30, you have to do a normal probability plot. And then you're also looking at that they have equal population standard deviations, or they're roughly equal. So they don't have to be exactly the same. It can be depending on the numbers that you're looking at. Like if you're working with very large numbers and you have one where the sample standard deviation is or the population standard deviation is like 52 and the other one is going to be 55, that's pretty close. When we're talking about different population standard deviations, now we're talking about like one population standard deviation might be 50 and the other one might be 12. So you'll know that they're either close together or that they are definitely far apart. Then you have to determine, is it going to be two-tailed, is it going to be left-tailed, or is it going to be right-tailed for your alternative hypothesis. The significance level, again, is always going to be provided to you, and then we need you to compute the value of the test statistic. So you are going to use the equation that you've been seeing on the past couple of slides, and then don't forget that you have to use the pooled sample standard deviation for your test statistic. So you actually have to compute this first before you can find your t-test. I am going to let you know right now, whenever we're talking about the test statistic, dealing with t, you do not have to use the p-value approach. I do not require you to do that p-value approach at all, because you will have to use technology, and it'll actually say obtain it exactly using technology. I don't require that. If you do, that's awesome, but it is definitely not required. So what you'll do is then, again, we are going to remind you for your DF, it is going to be the sample sizes added together minus 2. And then you also have to determine, is it two-tailed, left-tailed, or right-tailed, because that is going to depend on which column you're looking at in your table in the back of the book. If the value of the test statistic falls within the rejection region, you're going to reject your null hypothesis. Otherwise, you do not reject your null hypothesis. Don't forget, this is your value of rejection. So here at the 5% significance level, do the data provide the sufficient evidence to conclude that the mean salaries for the faculty in the private and public institutions actually differ? So I'm going to go ahead and use orange for sample 1 for the private institution. So for the private institution, you have a sample mean of 98.19. You have a sample standard deviation of 26.21, and you have a sample size of 35. We are going to use green for sample 2, the public institution. That sample mean is 83.18. The sample standard deviation is 23.95, and your sample size is 30. So this is a perfect example where your two sample standard deviations, they're close, but they're not exact. And they're close enough to where we can go ahead and use this pooled version. First, what we have to do though, technically you don't have to, but here's an example of what they would look like with a normal probability distribution chart in that box plot. So it gives you, for our private institution, it looks like it's about linear. You know, you're pretty good with that. And then with our public institution, again, it's pretty linear. We're good with that. And if you were checking to see, these are all about equal, roughly equal. Here again, they look like they're fairly equal. So it's safe to use this procedure. So here again, we do know that this is going to be a simple random sample, so we're okay to move forward with it. They're both independent samples, so assumption number 2 is good. The sample sizes are both over 30, so they're large. we can go ahead and move on with that. And the sample standard deviations are pretty close together, so we can go ahead and we can move forward with our pooled t-table. So just to recap, this is what we already know. We already know that we want our two population averages. Our null hypothesis is that the mean salaries are the same. Our alternative hypothesis is that the mean salaries are different. Again, we are going to notate that it is a two-tailed test, and then our significance level is going to be at 5%. Don't forget that because it is a two-tailed test, when we're looking at our t-value column as to which column we're going to be going with, we have to divide that number by 2. So we're actually going to be looking at that column that has 0.025. So here comes the lovely math calculation. We have to compute SP, and then we also have to compute T. So when it comes to SP, I'm going to go ahead and open up a different program. So that way it'll allow us to, actually let's do this. So I'm just going to go ahead and write down our differences. So we have the private, and you have your sample average is 98.19. You have the sample standard deviation, which is 26.21, and you have the sample size of 35. You have your public education, and your sample mean is going to be 83.18. The sample standard deviation is going to be 23.95. Your sample size is 30. And first, what we need to do, we need to first find the pooled sample standard deviation. So I'm going to write down the equation, and it's going to be N1 minus 1 times your sample standard deviation for population 1, and that's going to be squared, plus your sample size for population 2 minus 1 times the sample standard deviation for your second sample. And then we're going to divide that whole thing by N1 plus N2 minus 2. And then we take the square root of that whole big thing. So now it's just substituting those values in. So in substituting those values in, you get 35 minus 1 times 98.19, or I'm sorry, 26.21 squared plus 30 minus 1 times 23.95 squared. That square root needs to be extended, and then it's all divided by 35 plus 30 minus 2. Showing the next step. When you actually square everything, you have the 34 times 26.21. Let me go ahead and put a multiplication symbol. Plus 29 times 26.21 23.95 squared, all divided by 63. Next up, I'm going to actually use the exponents. So don't forget, you have to do your exponents first. So you're going to do 26.21 squared first, and then multiply that by 34. That will give you your 23,356.7794 plus, and then if you do 23.95 squared, then times 29, you get 16634.4725. And again, it's still all divided by 63. So when you combine that, we're making some progress. You get 39991.2519 divided by 63. Then you do your division. And that gives you the square root of 634.78. And when you take the square root, your pooled sample standard deviation is going to be 25.19. That's a lot of work for one small number. All right, and I am going to duplicate this, and I'm actually going to bring that all the way back up to the top. We're going to get rid of the square root symbol, because now we have to use our pooled sample to fill into this equation, our test statistic. So we have x, the mean of x1 minus mean of the second second sample, all divided by your pooled sample standard deviation times the square root of 1 over your first sample size plus 1 over your second sample size. So let's go ahead and substitute all those numbers in. We have the sample 1 average minus the sample 2 average, all divided by. Then we have our 25.19 times our square root of 1 over 35 plus 1 over 30. So with the numerator, that will give you 15.01 when you find that difference. And then when you add your fractions first, take the square root and then multiply by 25.19, you get 6.27. And when you divide that out, you get your test statistic of 2.39. That went much faster than finding the pooled sample standard deviation. But that's our test statistic, and that's something that we're going to need in order to determine if there is or is not a difference between private institution salaries and public institution salaries. So now I'm going to go back . And here I'm just going to refresh. We have our test statistic that we calculated as 2.39. But what I want to point out is that our DF, okay, our DF is still going to equal 35 plus 30 minus 2. So our DF is 63. It's a two-tailed test, so we're looking at that 0.025. When you find that in your column, you're going to get 1.998. Sorry, you guys, my cat's trying to get in the middle. So we have that critical value cutoff at 1.998. And our test statistic falls in that reject area. So we are going to be rejecting our null hypothesis and accepting the alternative hypothesis that a difference in fact does exist between our public institution salary and our private institution salary. So what I want to show right here, at the 5% significance level, the data provide sufficient evidence to conclude that a difference exists between the mean salaries of the faculty in private and public institutions. Whenever I'm asking for an interpretation, you can use that exact same interpretation. You just need to change the numbers as you see fit. So our next question that we have to answer is, we found that a difference does in fact exist, but we want to know how much is that difference. So that's where we're going to be kind of doing like a confidence interval, where we're going to be adding and subtracting again. But we have that as our confidence interval for our mean 1 and mean 2. And again, this goes with the pooled t-interval procedure. So as long as you're looking at roughly equal population standard deviations, this is going to be pretty close. So here it says that the pooled t-interval procedure, okay, what do we have to do to actually find what that value is going to be? It says obtain that 95% confidence interval for the difference between your means. Don't forget that you have to add your sample size together and divide or subtract from 2 for your DF, and then we're also going with the alpha divided by 2, so that's going to be that 0.025. We already know from our previous example that our t-value is going to be 1.998. So when we're looking at what our range is going to be for that difference, we're going to take the difference between our two population sample means, or I'm sorry, the two sample means, which we know is 15.01 from before, plus or minus the 1.998. And then this right here, when we're looking at this, that right there is from the denominator of our previous slide. So don't forget, if you go back to slide 23, from slide 23, we already know that that is going to be 6.27 because that was our denominator in calculating that test statistic. So you get 15.01 plus or minus 12.53. And when you subtract the difference, you get 2.49. When you add 12.53, you get 27.54. So what does that actually mean? Well, that interpretation is going to be on our next slide. And that is actually going to be, we can be 95% confident that the difference between the mean salaries of the private and public institution is somewhere between, because remember we had it in thousands, so we put it as a decimal to kind of cut down on those numbers. So it would be roughly between $2,490 and $27,530. So we can be 95% confident that the mean salary of private institutions exceed that of public institutions by somewhere between that value. I'm going to skip the next slide. So for slide 29, we don't have to worry about that because, again, for the purpose of class, we're not covering the Mann-Whitney test. So here we're talking about for inferences of two population means using independent samples where the standard deviations are not assumed to be equal. So this is where I was talking about how it is going to be a noticeable difference between the two standard deviations. So we have our same test statistic calculation from before. Remember that we don't assume that there's a difference between the mu's, so we're good with that. But then we have this lovely thing called delta. Delta is another monstrosity of a formula. So we have to be very careful at how we are setting things up and how we are calculating as well. Delta is going to be the degrees of freedom when we have two very different standard deviations. One of the big things I want to point out is that with your delta, you are going to round down to the nearest integer. So even if your delta is 19.99999, you are going to round down to 19. Because again, it will take more error into consideration there. So you want to round down. For the procedure, it's going to be the same, simple random sample, independent sample, but here the normal populations, large samples, and you also have to take a look that the two standard deviations, they are not close at all. You still have your two-tailed, you still have your left-tailed, you still have your right-tailed. You still have your test statistic calculation. Once you figure out the value of the test statistic, then we have to go into our critical value. So with that critical value, that is where our delta is going to come into play. We need to figure out what is our delta in order to find our test statistic critical value for two-tailed, left-tailed, or right-tailed test. So with neurosurgery operative times, several neurosurgeons want to determine whether the dynamic system reduced the operative time relative to a static system. And they looked at some data that's displayed below for the different operative times. And these times are in minutes for the two different systems. At the 5% significance level, do the data provide sufficient evidence to conclude that a mean operative time is less than, or the mean operative time is less with the dynamic system than it is with the static system. So we want at the 5% significance level. So it's not saying that they're not equal to. In this case, we're actually saying that it is less than. So because it's less than, I'm already noticing this is going to be a one-tailed test. At the 5% significance level. So alpha is going to be 0.05. I'm noticing that here we have 2, 4, 6, 8, 10, 12, 14 samples, and we have 6 samples over here. So these aren't large samples. Since they're not large samples, we have to do the normal probability plot to see, are these actually relatively normal in distribution? So here, it's roughly normal. Here again, roughly normal. So we're going to go ahead and do this. There's no outliers. As you can see, they've already calculated our averages for us for the 2 different samples. The sample standard deviation, this is what I was talking about, where you will obviously be able to see that it's different. So you have 84.7 and 38.2, not even close. And then you have N is 14 or N is 6 for your sample sizes. You can also see right here with the spread. So the spread is way far apart. So that's why you get a much larger standard deviation value for your dynamic system. And then the static is going to be much closer together. And because of the fact that it's much closer together, that's why the sample standard deviation is 38.2, where it's much smaller. So now we have to try to figure out, okay, well, is the dynamic better than the static? So let's go ahead and let's actually put things into place. So we have to do our null and our hypothesis, our null and alternative hypothesis statements. So our null, again, is that there's absolutely no difference between them. Our alternative hypothesis is that the mean dynamic time is less than the mean static time. We need to note that the test is performed at the significance level of alpha at 0.05 or 5%. And we are going to use this equation right here, gotta love this equation, to find our test statistic. And we are going to do that using our data found here. So I'm going to go ahead and give you a moment. You can pause the video. I'm going to show you how to get the answer as well in just a moment. So going back over to our earlier notes. We would have our dynamic mean is 394.6. Our static mean is 468.3. And we're dividing that by the square root of our dynamic standard deviation squared over our sample size plus our static sample standard deviation squared over our sample size. So just to kind of condense this down, our numerator is going to be negative 73.7. And our denominator, so again, if you do 84.7 squared and then divide that by 14, you get 512.435. If you do 38.2 squared and then divide it by 6, you get 243.207. You're going to add the two together. Numerator doesn't change. Take the square root of 755.642 and you get 27.49. And when you actually divide that out, you get your test statistic is negative 2.68. We definitely need to know that 2.68. Because now we get to find our critical value using delta. So I am going to go ahead and write down our DF, or delta, is going to be equal to, here's our, I'm actually going to write this down. So you have the sample standard deviation for population 1 squared divided by the sample size plus our standard, why does this keep doing that? Oh my God, this is gonna kill me. Why is this doing this now? Okay. And then you have the sample standard deviation of the second sample, and you're going to square that, and it's all over the sample size for sample 2. Okay. That being said, it's actually, we're going to put parentheses around it because of the fact that this whole value is going to be squared also. The whole thing is squared. Then we also have to do, in our denominator, our standard deviation for the first population squared divided by the sample size for the first population, and then we're going to square that whole thing. But then we also have to divide it by the sample size minus 1. We also are doing the sample standard deviation for sample 2 squared, all divided by your sample size of the second sample. We're squaring that whole thing, and it's all over the sample size for the second sample minus 1 as well. So it's a lot. How does that look for us? So substituting all those values in, you get 84.7 squared divided by 14. You're adding that to 38.2 squared, all divided by 6. That whole thing is squared. Substituting it in again, you have 84.7 squared divided by 14, and that whole thing is going to be squared all over 14 minus 1 plus you have the 38.2 squared all divided by 6, but then that whole thing is squared all divided by 6 minus 1. So that's how everything gets entered. My advice to you is to go ahead and calculate this portion first, rewrite your numerator, and then square it. And then when you're doing the other ones, do this first before dividing it. Once you divide it, then put it back in your numerator. Or I'm sorry, your denominator. Because your final answer is going to give you 17 point something. So when you round down, you actually are going to get a DF of 17. You have your DF of 17. Alpha is going to be 0.05. And when you do that, we have to make the comparison because here it shows you at 0.05 with a DF of 17. So remember, it's a left-tailed test, so we're looking at negative 1.74. We came up with our test statistic at being negative 68. That again falls in this region right here. So we are going to reject our null hypothesis and we are going to accept the alternative. There's enough evidence to reject that null hypothesis. So we are going to say that yes, we do know that the dynamic system is better than the static system. It saves time. And when you're talking about operating rooms and you're talking about being put under with anesthesia, the less time you're under with anesthesia, the better. Also, the shorter the surgical procedure, the more available doctors and nurses are for other procedures as well. So here's that interpretation. At the 5% significance level, the data does provide sufficient evidence to conclude that the mean operative time is less with the dynamic system than with the static system. So now the next thing we have to ask is, but by how much? If it's by 5 minutes, is it really worth switching everything over to save 5 minutes? Maybe, maybe not. If it's 20 minutes or 40 minutes, is it worth doing that? Well, now we're getting closer to where we might want to consider it. The nice thing is that we already have our delta, this horrible equation right here, because it is a monster and you have to be very careful with how you are getting through it. We already know that that is going to be 17. We already know, here it's saying with a confidence interval, we want to know, it's on the next slide, but we want to know at the 90% confidence. So when we're looking at that, you have alpha is going to be 0.10, but remember, all confidence intervals, you have to divide by 2. So this is what we need right here, because where we're looking on our table, DF is going to equal 17, and we're looking at the 0.05 column. That's going to make a difference. We have our formula right here to show us how to get our confidence interval to see how much faster the dynamic time is over the static time. So here's that operative time again. So we want to say a 90% confidence interval for the difference between the two population averages between the dynamic and the static systems for operative time. So here is just what we were talking about. Alpha is going to be at 0.10, but we have to divide that by 2, so it's really at 0.05. Our DF was 17, so our value that we're going to be using is 1.740. So we already know the differences in our two sample averages. We know that that is going to be negative 73.7. That's our numerator from when we were calculating out our test statistic. Plus or minus 1.740. And then again, we already calculated the square root of S1 squared divided by N1 squared plus S2 squared divided by N2 squared. That's that 27.49. That right there is going to be on slide 36. So again, if you go back to slide 36, you'll see where we got that number from. And then we just go ahead and we calculate. And we come up with a range here. And we're going to interpret our results, but basically what this is saying is that the dynamic system is going to save you between a half hour and 2 hours worth of time than the static system. So again, that dynamic system will save you about a half hour to 2 hours more than if you use the static system. And when you're a doctor or a nurse and you're saying that, okay, well, I can save a half hour of my time, or I could even save up to 2 hours of my time and use that somewhere else, I think that that's worth it. So here again, notice how with time, we don't talk about time in terms of negative value. So that's why I said that it's going to be somewhere between roughly a half hour to 2 hours less. So it's going to be, we can be 90% confident that the dynamic system relative to the static system reduces the mean operative time by somewhere between 25.9 minutes and 121.5 minutes. And again, you don't have to change any of the wording, just change the values and you're good to go. And then when we're talking about wrapping it up, you just have to remember when you're talking about a pooled versus a non-pooled T procedure. So just to kind of recap, with that pooled procedure, that is where the two standard deviations are pretty close to each other. That non-pooled procedure is when the standard deviations, you can see a difference in that value. That non-pooled procedure is where you're going to have a huge monster of an equation for your delta. And again, that's when the standard deviations are very different. If you guys have any questions or get stuck with anything, just go ahead and make sure to